the opportunity to emphasize this last section of the text. And the reason is because if there's anything that you take away from this particular segment that's clinically relevant and something that you're going to be able to, going to be expected to be able to do, it's being able to differentiate between a metabolic acidosis and alkalosis and a respiratory acidosis and alkalosis. And the key to understanding that determination is all in the carbonic anhydrase equation up here on the upper left-hand corner of our slide here. Carbonic anhydrase mediates the conversion of CO2 and water to carbonic acid, which then becomes bicarb and protons, and it also, of course, mediates the reverse reaction as well. And where this reaction comes to steady state determines what your plasma pH is. So, and that's where our Henderson-Hasselbalch equation comes from. The pH, the proton concentration, dependent upon the PCO2 in your blood gases and your bicarbonate concentration. Now, if you want to make a determination about what sort of acid-base problem you're dealing with, the very first thing that you have to do is look at the pH of the plasma. And I know that that makes sense, but you would be surprised at the number of students who are given a problem and skip over that part and try to determine what they have on their hands without actually looking at the pH of the plasma first. If the plasma pH is low, then you're dealing with an acidosis, obviously. And the next thing that you want to know is what's causing that acidosis. So you will look at your blood gases, you'll look at your PCO2, and you'll look at your bicarb concentration in the blood. And in this case, I'm going to say that both are up. And now the question is, which of these two is causing the acidosis? Well, if we look at bicarb here in our carbonic anhydrase equation, high bicarb is going to shift this equation to the left. And what that's going to do is it's going to eat up protons and generate more CO2, which is blown off in the lungs. So high bicarb will actually cause your plasma to be more alkaline. On the other hand, high CO2 will drive this equation to the right, and that will generate more protons and cause the pH to drop. So when you're looking at these two parameters, the pH is dropped. A rise in CO2 is what must be causing that pH to drop, because of these two parameters, that is the one that will cause an acidosis. The bicarb is up because it's a compensatory mechanism. In response to the acidosis, your kidneys are trying to conserve bicarb, and bicarb has risen in the blood. So the pH is still down, but because of the compensatory mechanism, it's not down as far as it might be where the kidney is not operating. So this tells us that we have a respiratory acidosis. That is, the cause of our acidosis is respiratory, perhaps a low breathing rate or something that is limiting respiratory function and causing our CO2 to build up in the blood and rise. Okay. On the other hand, if we have a low pH and acidosis, and now we look at the situation where both of these parameters are down, again, we look at low bicarb, and a drop in bicarb is, again, going to shift this equation to the right, and it's going to generate more protons. It will cause an acidosis. A drop in CO2 will shift this equation to the left, and that will cause protons to be eaten up and CO2 to be generated, and so that will cause an alkalosis. So if we ask now which of these parameters is causing our acidosis, the low bicarb, either due to diarrhea or due to some sort of a kidney problem or something like that, is what's driving this pH down. Because of the two parameters, it's the only one that will actually cause an acidosis. The drop in CO2 in this case is respiratory compensation. You're blowing off CO2, your CO2 is dropping and therefore what we have on our hands is a metabolic acidosis. If we look at our plasma pH and our pH is up, then that means we have fewer protons. We know that we are dealing with an alkalosis. And if we look at our parameters, again, both of our parameters are down, so we ask ourselves which of these is going to cause an alkalosis. A drop in bicarb is the one that once again shifts your equation to the right and generates more protons. And if we a drop in CO2 shifts this equation to the left and eats protons up, that will be what will cause our alkalosis. If we look at our Henderson-Hasselbalch equation, a drop in PCO2 is going to actually cause this pH to rise, because this parameter will rise and the pH will rise. So if we look at the Henderson-Hasselbalch, that also tells us that it's the drop in CO2 that's actually going to cause our pH to go up, and our drop in bicarb is compensatory. Our kidneys are excreting more bicarb in a compensatory as a compensatory mechanism, so we're dealing with the respiratory alkalosis. If we look at our pH, again, our pH is up, and now both of our parameters are up. We know now that it's the rise in bicarb that's going to drive this equation to the left. It's going to eat up bicarb. It's going to cause our pH to go up. And again, if we look at our Henderson-Hasselbalch, a rise in this bicarb parameter is going to cause a rise in our pH. So we know that we are dealing with a metabolic alkalosis, and the CO2 is up, but we know that that's compensatory because a rise in CO2 drives our equation to the right and generates more protons, not less, and it's actually causing our pH to drop. So our pH is still rising, but it's not up as far as it would be were our lungs not allowing CO2 to build up in the blood. Okay, so this is a fairly important thing for you guys to be able to do. Clinicians will ask you to do it, and you should be able to look at these three parameters and tell them what sort of an acid-base problem that you're dealing with, and that will tell you what sorts of problems you might be dealing with, whether it's in the kidney or the intestines, or whether you're actually dealing with a respiratory problem.